TTL Computer 2. Today, we're going to zoom out and look at the high-level view of our digital simulation design, just to complete our design and to get us to the point where we'll be ready to turn on this computer in our next video. Okay, so just quick review. Here's our register set that we looked at last time. That's all good to go. Here is our memory address register and our program counter that we looked at earlier. They're all hooked up to our control signal tunnels. Our data bus is connected, and also to our address bus tunnels. Program counter likewise hooked up to the control signals, our data bus tunnels, and the left bus tunnels as well. Okay, and then our RAM and our ROM that we looked at in our last video as well, all hooked up in the tunnels. I updated the memory decode logic here just a bit, so it's solid and completed for our production build, where it's basically the ROM is active at less than 2000 hex, and our 32K RAM again is memory mapped at the upper 32K bytes at address 8000 hex. Okay. And then just to review some of our other circuits that we looked at, right? Here's our control unit, all hooked up to the instruction tunnels. We have our flag tunnels set up, our run flag tunnel, and our tick counter tunnel as well. And all of our 24 control signal tunnels are connected as well. We have our arithmetic and logic unit all connected up, right? Our 3 ALU control signals, our left and right bus tunnels, our data bus tunnels. Now, this is something new, right, that we haven't seen before, but this is our flags register, and this is just using our 4-bit counter to implement this. And we just take the 3 flags from the ALU, and those are stored in the flags register based on the flag in signal and the P clock. And again, so here's the output from our flags register feeding our the appropriate tunnels, and then we have our carry flag that is fed back in as a carry input to the ALU. Okay, and then we have our tick counter. So we spoke about this briefly when we looked at our counters. This is just implemented with our basic 4-bit counter. And we have a little bit of logic here as to when the clear of the counter can take place. And the counter can be cleared either from a manual clear signal or from the tick reset signal from the microcode. So either of those two signals, right, would reset the counter to 0. And then the output of the counter is the T tunnel, or the tick counter tunnel. Okay, so that kind of rounds out the things that we've looked at before, except for the clock. Okay, so here's our clock that we've looked at before. This is hooked up to the appropriate tunnels, right? The P clock, the U clock, the T clock, and the not clock tunnels, as well as our active low run signal that really shuts, everything down, shuts the whole computer down if that goes high, right? And then our inputs to our clock. Here's our real oscillator, our system oscillator, and this is going to be a 4 megahertz oscillator once we get to our build. But using digital, we can either clock this thing manually, or we can set a given frequency for that oscillator. And we'll see that once we turn the computer on. And then this is our reset button. So we can reset the count, reset the system here. And we'll actually need to hit the reset button once we turn the computer on to get everything synchronized and actually get the computer started running. And then we have our program and our run signal, right? That also goes into the clock circuit. And we saw how that signal stops the clock when it reaches the the appropriate point, which is the start of the not clock cycle, and then would set the computer into its not run state as well. Okay, and then up here, we're really completing our bus designs here. And you see that we have our 4 buses. We have our address bus, we have our data bus, and we have our left bus and our right bus. So what we're doing here is really doing, we're adding in any pull-up or pull-down resistors that we need for our buses. And both our left bus and our right bus we use pull-down resistors because we want these buses to go low to 0 when they're not being actively driven, right? And that's important for when we are moving data from the left bus to the data bus through the ALU. You'll remember that when we do that, we want to, we use a logical OR operation, and that whatever data is coming from the left bus, when we OR that, we want to make sure that the right bus, floats to 0 when it's not being driven, so that we get a good data transfer through the ALU. And then we are using pull-up resistors on both our data bus and our address bus. So here we just have a single pull-up. You see that the data bits are 16. So we're only depicting one resistor, but there's really 16 because the address bus, right, is a 16-bit bus line. Okay, and then these little input, right, the square is a circuit input that allows us to inject data into the bus, right? So if we're in program mode, right, we can use these to set data values on the bus manually, right? So that's both for the address bus and for the the data bus as well. Okay, so that really rounds out our implementation. That completes everything. Our digital simulation is fully implemented at this point. Now, I have a couple other constructs that I've put together to aid in for us to see what's going on. And these are some display units I've put together. They're just connected to the different buses, the instruction bus or the instruction register output, the left bus, the right bus, and the data bus. And we just have some hex displays on here so that we can, monitor what's going on the different buses. And then I also have some switches down here that, again, when we're in program mode, will allow us to drive low the different control signals, so we can examine what's the value of the A, the A, the B, the C register, the X register, stack pointer, our RAM, and our counter, program counter. We can look at those values using these switches and the display units here. Now, I also defined our first device for TTL Computer 2, and that's a 2-digit hex display. And if you recall, all of our devices are going to be memory mapped. So this is basically a write-only device. So we can write to address 2001, and that will get latched in with this hex display, and we'll be able to display that data on the hex display. And then we can just briefly look at this. So all this is just an 8-bit register, right, connected to the data bus. And we have a little bit of a decode logic here that decodes, looks at our address bus and decodes the address 2001. And if the write signal is brought low and the address is 2001, it clocks it'll clock in the data on the data bus and send that to the hex displays. Okay, so that's it. That's our system design. We are fully implemented and ready to go. And this is kind of my this is kind of my running view right here. This is kind of what we'll look at when we kind of run the computer. We'll, we'll start up, and you see everything goes active here. And all we need is our clock to be going. But we see that we can see our address bus values here, and we can see our instruction register. We can, on the hex displays, we can see what's on the left bus, the right bus, and the data bus. And we can also, clock the computer manually here. And right, we could switch into program mode, and these switches would be active. But that brings us back to ready to run, and that's really going to be where we're going to pick up our next video, is that we're going to start to clock this computer and see if it works and if we can actually run a program or not. So that's going to wrap it up for us today. So until next time, that's it. Thanks for watching.